Think I'm going to record this meeting, and if you want to leave earlier, I will upload this video on the YouTube channel. So today I'm going to talk about the magnetic force. The magnetic force on the moving charge and the current follows different equations. So I'm going to discuss these two cases separately. And then I'm going to talk about the torque. If we have a current loop, in a magnetic field, then the loop will spin or rotate periodically, and we can using this this model to make an electrical motor. And I think at the end of the class, I'm going to show you a video how to make an electrical motor, and this is very interesting. So first of all, let me talk about the magnetic force on a moving charge. This is a question on the motion physics due yesterday, and you find that we have a moving charge. This charge has positive sign and a negative sign. Different sign follow different rule, and they are moving with a constant velocity. So we know the velocity is v, and they just enter a magnetic field. This magnetic field is inward or inside of the paper, and this is outside of the paper. And you can also find that the magnetic field is perpendicular to the moving speed, to the velocity. Okay, in this case, we will find that this charge is going to move without a linear motion. It will be change the direction, and you will see there's a depletion for the charge. But we are going to figure out why the charge have a force. And here I just show you some easy diagram to help you understand why there's a force on the charge. We know the charge, if has a speed, a moving charge is going to generate a magnetic field in the space. And we know the magnetic field generated by the charge has an equation. It's proportional to the charge and velocity and cross the distance over the distance square. And if we are going to test the magnetic field at this point, we just connect these 2 points, and we get a unit vector of the radius, and the velocity is going to the right, and we use right-hand rule, and I just curl my fourth right finger from V to the R and counterclockwise. Then the direction of my thumb is the direction of the magnetic field. So the magnetic field goes out. So on this side, and magnetic field goes out. So this is magnetic field distribution on this side. The dot means goes out. And on the bottom side, and the magnetic field goes in. So looks like this. Okay, so this is a magnetic field distribution near a moving charge. And you can find that if this moving charge just enter a magnetic field, there is an external magnetic field. The black cross are external magnetic field. And you can find that this magnetic field is going to interact. So how does this happen? So if we use the right-hand rule to determine the magnetic field generated by a moving charge, you will find that the magnetic charge will have a force on the in the magnetic field. And in this case, if we have two magnetic fields, on the top side, this two magnetic field has opposite direction. So you can think about they attract each other. And on the bottom side, these two magnetic fields have the same direction, so they repulse each other. So that means the attract, one side is attract, the other side they repulse. So this charge is going to move up. So this is net force of the charge. So if we have a positive charge. So moving charge generate magnetic field. And if this magnetic field generated by the moving charge interact with external magnetic field, then there will be a magnetic force on the charge. And we call this magnetic force as Lorentz force, because this is an idea came from Lorentz. And he is a scientist, a physicist, and he derived the equation of the force on a moving charge in the magnetic field. So from the experiment, we can confirm that the generated magnetic force on the charge is proportional to the value of the charge and is also proportional to the moving speed and also the magnetic field. So this is the relation between the force to the charge, to the velocity, and to the magnetic field. If we write down this relation into equation, then we can write in this way: the force equal to the charge, a scalar, times the velocity, a vector, cross magnetic field. Okay, so this is the equation of a magnetic force on a moving charge. So the moving is very important. If the speed is 0, then the force is 0. There's no force on the charge. So on the positive charge here, in this case, the speed goes right and the magnetic field goes inside. So we use right-hand rule. I use my right hand, curl my forefinger from velocity rightward to the magnetic field, and my thumb goes up. So the force is on top. Okay, so this is the direction of the force. And let's go to the second figure. We have a negative charge. So if the charge is negative in the equation, we have to put a negative sign in front of the equation. It is negative sign. Okay, so we use the same right-hand rule to determine the direction, but we have to flip the direction because of the negative charge. So the direction of a negative charge is antiparallel to the direction of positive charge. Okay, so we still use the same rule. So the velocity goes up and the magnetic field goes out. So I curl my forefinger from velocity to the magnetic field. My thumb goes right, but I have to flip my direction. So this is the direction of my thumb. So this is the direction of the force. Okay, so this is how we determine the direction of the magnetic force on a moving charge. So for the figure A, and the force goes up. For the figure B, the force goes left, up, left. Okay, this is the result of this question. And I have more things to talk about for a magnetic force. So suppose we have a magnetic force and this magnetic field in the space, and you can also find there is a positive charge okay, in this way, and the moving speed is in this way. It's a speed. According to the force equation, QV cross B, what's the direction of the charge on the force on the charge? So from the V goes to the magnetic field, then I could determine the force goes up. Okay, so from this equation, we know force is always perpendicular to the velocity. So in the physics one, and if you still remember, if the force is always perpendicular to the velocity, then this object is going to move in a circle. So we will find a circular motion, right? If the force is always parallel to the speed, then the motion is a linear motion. Okay, this is a motion. If the force is a constant, goes down, and at the beginning, the velocity is perpendicular to the speed. The velocity is perpendicular to the force, but during the motion, the force doesn't change the direction, then you have a projectile motion, something like this, right? But if the force is always perpendicular to speed, not just at the beginning, but anywhere, then you will have a circular motion. Right? Suppose you have a string and contact with a ball, then the force goes in this way. This is a tension on the string, and the velocity is always perpendicular to the radius. So in this case, you will have a circular motion. The same idea in the magnetic field, the magnetic force is always perpendicular to the moving speed. So the charge is going to move on a circle. The trajectory is a circle, and with a constant radius. So this is the motion of a moving charge in the magnetic field. And let's calculate the radius of this circle. Okay, the radius of the circle actually depends on the centripetal force. Here's my note. Here. Okay. Let's see. So in the magnetic force, we have this one. This is the trajectory of the moving charge, positive charge. Speed goes up, the force goes inside, and we can write down the centripetal force to maintain this motion. Centripetal force. To maintain this regular motion, this circular motion is proportional to the mass of the charge, proportional to the velocity square over the radius. Okay, the radius of this circle is a centripetal force. And the centripetal force is provided by the magnetic force. So we have the magnetic force. This is equal to Q times the velocity times the magnetic field. So these two forces should be equivalent. Okay, so we just establish a relation equal to QVB. Okay, then we can solve the radius. Solve the radius, that will be equal to mv over qb. So that means if we know the mass of the charge, and we know the value of the charge, and we can measure the speed, then if we can measure the magnetic field, then the radius could be solved, is determined. So this will be a constant and a regular circular motion. Okay, do you have any question? Okay, if not, let me move to next part. Next question on the course side, on the mastering physics, will be number 11. If in the space we have both a magnetic field and the electric field, how does the motion of the charge look like? So here, this charge has a moving speed 10 to the positive 7 meter per second. Oh, here, this is speed. And this charge is inside two parallel plates. So the two parallel plate has a surface charge on side. On the top, this is a positive charge. On the bottom, there's a negative charge. And this charge, moving charge, is the electron. Electron is negative. Okay, there's a common sense. And in the plate, the electron is attracted by the up plate and repulsed by the bottom side. So in the plate, this electron is going to move like a projectile motion, like this. Positive, attract the electron, negative, repulse the electron. And inside the plate, the electric field is constant. So inside the plate, electric field is constant. So on the electron, there will be electric force equal to the charge times electric field. Okay, and the electric field goes up. This is the electric force. And the question is, if we don't want this charge change the direction, we want this charge move straight, and there's no depletion, we need to apply a magnetic force inside this two plates to balance the electric force. So if we just draw the free body diagram on the electron, we can find the electric force goes up. So we need a magnetic force to balance the electric force. The magnetic force goes down. Okay. And if the magnetic force goes down and has the same magnitude, then these two forces cancels and the charge will move straight. Okay, this is our objective. So we need to apply a magnetic field to generate a magnetic force going down. According to the magnetic force, we have QVB. Right? This is magnetic force. We need a force perpendicular to the velocity and also perpendicular to the magnetic field. So we have two options. So magnetic field, one goes in or goes out. Yeah, let's discuss this two cases separately. If the magnetic field goes in, oh shoot, get it wrong. This goes out. This goes in. Okay. So if the magnetic field goes out and the moving speed is in this way, and this is a negative charge. So negative charge, we have negative sign in front. Let's use the right-hand rule to determine the direction of the force. Okay, so I curl my forefinger from velocity to the magnetic field, then my thumb goes down and the force goes up. Okay, this is the force, magnetic force. And the same thing if the magnetic force on the right side, the moving speed goes right, but the magnetic field goes in, then my thumb will goes up, so the force goes down. So The second case satisfy our condition. So our requirement is to apply a magnetic force going down. So we are going to apply a magnetic force goes in. Okay, so this is the direction of magnetic force, magnetic field. Then let's determine the magnitude of the force. If these two forces are equivalent, then the charge times the electric field should equal to the magnetic force on the charge. And you will find the charge goes out, cancels. This is independent to the charge. So the magnetic force, the magnetic field is going to equal to the electric field over the speed of the charge. Okay, so this is the solution. B equal to E over V. Then let's go back to this question. So the first one, what's the magnetic field strength will allow the electron to pass between the plates without being deflected? We use electric field over the speed. Okay, then what's the electric field? We know the voltage. So let's see. Where's the voltage? Here. We know there's two plates connect with a battery. The voltage of the battery to 200 volts. That means the potential difference between these two plates is 200 volts. And we also know for the uniform electric field, and the electric field is equal to the magnitude equal to the voltage over the distance. The distance in between is the spacing 1 centimeter. Okay, so we have 20,000 volt per meter. This is the magnitude of electric field. Okay, so if you don't remember the equation right here, electric field equal to the change of the potential over the distance. Okay, then we have the electric field over the speed. Then we got the magnetic field. Second one, what's the directional magnetic field? I just derived that should be into the page. Okay, if we have negative charge moving this way, then the magnetic force goes down. Electric force goes up. Okay. Do you have other question?
Just double checking, you said that B is proportional to, B is equal to the magnetic field is equal to the electric field over velocity?
Yeah.
Okay, thank you.
So this only apply in this case. If we need the charge moving straight, so we need the two force balance, right? So this two force, there's an electric force, this is a magnetic force. If this two force balance, then we have this relation. Okay, and then let's talk about the current in the magnetic field. Just now we talk about the charge in the magnetic field. Now, let's talk about okay. So if we have a current, this is a magnetic field, and we have a current, the same thing, and inside the magnetic field, and the current goes up, and the same thing, the current is going to generate electric field, and the direction should be a circle. So on the left side, it goes out, and on the right side, the magnetic field goes in. So the same thing, if the direction are antiparallel, they attract each other, and if they have the same direction, they're repulsive. So the current is going to move to the left. So there will be a force, magnetic force, on the left. Okay, then how does the force look like? The force from the experiment is proportional to the current and is proportional to the length of the current inside the magnetic field. So in the reality, the magnetic field has a region. So there's a border. I use another color. So there's a border of the magnetic field. So if the current is very long, we only consider the length inside the magnetic field. So this will be the length of the current, and the direction of the length is the direction of the current. So we use a vector of length inside the magnetic field. Okay, and this is also proportional. The force is also proportional to the magnetic field. So if we write down this relation as an equation, then the force is equal to the current times the length inside of the magnetic field cross the magnetic field. Okay, but still we use the right hand to determine the direction of the force. You will find that the L goes up and the magnetic field goes in. So my thumb goes to the left. Goes left. So the force goes to left. Okay, this is how we determine the direction. So if in the magnetic field we have a loop of the current, so we have magnetic field and we have a current loop, and the current goes up, down, left, and right. So this is a current. Then each side of the loop will has a force on the current. So according to the, just now we talk about the direction of the force here. If the current move up, if the current move up, the force is going to point left. So that means we have a force on the left, this one. Then the same thing on the top side, we can use right hand to determine the force that will be goes up. And on the right side, the force goes in this way, and bottom side, the force goes in this way. So that means in this case, each side has a force, but the net force will be force on the left plus force on the top, force on the bottom, force on the right. And you will get 0 because the current is the same and the length is the same, magnetic field is the same, but the direction are antiparallel, so the net force is 0. Okay, but let's check the torque. If this loop has an angle between the magnetic field, not perpendicular, in this case we see that the magnetic field is perpendicular to the surface of the loop. But if the magnetic field has an angle, not a 90 degree, for example, I use a color. This is magnetic field, goes up, and we have a current loop in this way. This is a front view. Okay, the front view. If there's a front view, direction is wrong. Direction goes down. We look at this loop in this way. Okay, in this way. So like this. So on the left side, the current is going into the page. And on the right side, it's out of the page. And the degree is not 90 degrees, but we still have a small angle to make sure the force is not equal to 0. Okay, let's check the force on the left side and the right side. And let's see, the magnetic field goes down and the current goes out. Do I got it right? Oh, this is not right. This is in, this is out. Oh, this will be correct. Okay, so the current on the left goes in, then the B will be equal to give a force. The force is on the left. This is force. So the same thing. The force is here. The force is on the left. And on the right side, the force is on the right. Okay, goes right. Then in this case, you will find the net force is also equal to 0, but the force and the loop has an angle. If there is an angle, then the force is going to rotate this loop. So we say the torque. On the loop. So the torque on the loop, then the loop is going to spin in this way, right? Counterclockwise. So we are going to use this to determine how large is the force and how large is the torque. We know the torque has a relation with the force times the radius, right? So we can derive this and get the torque is proportional to the current. If the current is large, then the torque is large. And also perpendicular to, this is also proportional to the surface area of the loop. So if the loop is large, then the torque is large. If the loop is small, the torque is small, and also proportional to the magnetic field. And if we write down this relation into an equation, then the torque will equal to the current times the surface area, if this is a vector, times the magnetic field. Okay, here I want to talk about how we define the direction of surface area, right? And if we have a loop, so the loop goes clockwise, is the current, then the magnitude of the surface area, that's easy. That's the area of this region. But how about the direction? We use right hand, our forefinger curl clockwise, and my thumb goes down. So the direction of the A goes down. If the direction is counterclockwise, then I use right hand, curl my forefinger counterclockwise, then the area goes up. Okay, this is how we define the direction of the area. And if we have a magnetic field, for example, like this is a magnetic field, then let's use this equation to determine the torque. The torque is from A cross B. A goes down on the left side, A goes down, and the B goes right. Then the torque is going, let me see, going out of the page, out of the page. This is a torque. Okay, and the same thing, if the loop in this way, B goes right, A goes up, the A cross B, So the torque goes in. This is a torque goes in. Okay, and also we have another name for the I times A. Okay? We call this as a dipole moment. This is just a name, so we use a little mu to represent the dipole moment. So the torque could be written as a dipole moment cross B. So this is just to help you to memorize this, but you have equation sheets, so you don't need to memorize this. I tell you that I times A is called dipole moment. Okay, this is a torque. And how does this useful? Why we need to talk about this? I show you some interesting things. We can use this to make an electrical motor. Motor here. So there's a loop, and for the motor, here's the motor. Now this one. Okay, so this is a motor, and if you have a toy car and you make some battery inside, and you just remember the car, you will say there's a motor. So how does the motor work? I show you. So here, the motor has a loop, and the loop connects with a battery. And on the left and right, there are magnets. And the magnets generate magnetic field from left to the right. And you can also see for the loop, the current on the left goes in, on the right goes out. And the force, magnetic force, goes up and down. So there is a torque. You see, the torque is going to spin this loop. And when the torque when the torque equal to 0, they just switch the direction of the current by using the rotator. So it maintains the spinning of the loop. So the loop is spinning. So the principle is easy. We use magnetic force, and the magnetic force on the current could be generated by the battery. The battery provides the current, and the current will spin. Okay, so this is the principle of the motor, and we can use more loops. For example, like this, we use 2 loops and to generate more force, more loops, more torque, and the speed increase. So the real motor has a lot of loops, and we bond these loops together and make a package. Then this is the real motor. And you know, the Tesla use electric car to drive the car, and they don't want to borrow the gas. So if there's no gas, they want to use a battery, they need a motor. This motor is made by magnets, loop, and the battery. So this is how people use the electric motor to drive the car. Okay, this is application of the electric motor. Okay, so do you have any question? If not, let's move to the quiz. So the quiz we have, let me see, we have 10 minutes. I show you how to do the quiz. So on the course site, you can see the course site here, and you can see a quiz. I show this one, and when you click this one, you will see there are 4 small tables. So you fill in these tables, and actually you don't need to give me the value. You just need to tell me the direction of the net force and the torque. If the 0 or the torque is 0, and you just write down 0. So the direction I write here could be up or down, left or right, or in or out. So you just need to write this 6 words, pick one to write in the table. If the 0, you write 0. Okay, so 10 minutes after you finish, you're good to go. And don't forget, we have our exam next Monday.